hardness Vickers is about Rockwell C40, and 350 is about Rockwell C35. I told you in general you have a hard time getting cracking below Rockwell C30. Once you start getting into this 35 to 40 range, the problem with the HY130 Seawolf welds, I call them the HY130, the weld metal was sort of an HY130 weld metal. They were up there above Rockwell C40. Okay, that's why they were getting hydrogen cracking. Whereas if they had it was within the specification range for the welding wire, but it was on the high side. Everything, the carbon was at the high end of the range. The chromium was the high end. The nickel was the high end. The vanadium, everything was the high end, and so it really was an HY130 weld metal. And it had crossed the line, and you could get very high hardness. You have to make corrections for different welding different types of welding process. This is submerged arc welding, which has lots of heat input and therefore cools slowly. Shielded metal arc 1.5, gas metal arc 1.25. So you have to do some other work to correct for things, but then and hopefully you get something and you say, okay, I can make fillet welds or whatever welds and not have a big problem. However, the second method is hydrogen control, and they don't even use the same carbon equivalent formula. Why? Because this is the type of structural steels the Japanese started developing in the 1980s, and they came up with this PCM, which is a cracking parameter, P for parameter. Instead of silicon over 6 and manganese over 6, it's silicon over 30 and manganese over 20. They just take thousands of steels, fit them into a regression formula, plot them up, and see which ones crack and which ones don't. And this is what they did with lots and lots of data and computers to help them analyze it. Okay, but it's basically similar to the other carbon equivalent that we had. And that carbon equivalent, what did I do with mine? Anyway, oh, here it is. This one that you have a copy of, it will tell you under what conditions you might want to use one parameter versus another. But a lot of different people did research on this and came up with, everyone did their own regression analysis and stuff. But you now have to, in hydrogen control, you have to determine whether you have extra low hydrogen, or hydrogen is not controlled. And those are H1, H2, and H3. So H1 is if you have less than 0.2% moisture in the coating of your stick electrode. Here's your stick electrode. Low hydrogen, you need to know whether you have low hydrogen electrodes or non-low hydrogen. Remember, Stout and Doty taught us that 50 years before this. Low hydrogen, so this was extra low hydrogen. They've been baked out to get the moisture very low at 700 to 800 degrees F. We've talked about, you can only pick up 20 electrodes at a time, and you have to bring back the stubs and things like that. Low hydrogen is not 0.2%, it's 0.44%. And hydrogen not controlled, you can use cellulosic electrodes like a 6010, which is a different color coating on the outside. Welders recognize these things by the different coating colors, but the coating colors depend on the manufacturer, so there's, but if you're usually welding only one or two manufacturers' electrodes. Anyway, so you can have hydrogen levels H1, H2, or H3, and you now have to go later in this thing. Well, you also have to, I ought to explain this because it's in the same table. You have to determine whether you have low, medium, or high restraint. And this is not quantified. We don't know how much stress you've got, but if this basically says it's thicker steels or repair welds where the members can't move, okay? Like a circular patch, oh, that's very high restraint, okay? But a medium restraint might be a heavy plate, but it's allowed to take the V shape. It's not welded to other things on either side. Low restraint, it's either thin material or it's not already welded to other things. And so now you come to the tables, and the first table you go to is susceptibility index for the groupings. So here's your hydrogen levels 1, 2, and 3. You have to look at your carbon equivalent and determine whether you're an A through G region, depending on the hydrogen and the carbon equivalent. And then you go down to table 2, and you can read off your preheat. Okay? It will tell you how much preheat to use, low, medium, or high restraint, A through G. The highest they have on here is 320 degrees Fahrenheit. The lowest is less than 65, okay, which means no preheat, essentially. Usually it's only in the D and F where you're starting to get the fairly high, but if you have high restraint and greater than 3 inches thick, it's always 240 to 300, even if you have very low carbon equivalent. So it's a complex function. There's many variables. This turns out to be the simplest, and it just took me 10 minutes to just walk you through it, right? And if I was giving quizzes, this would be the perfect quiz question. What is the preheat for, right? And you could calculate it. Except it would take, for me, it would take me 10 minutes. It's going to take you a half an hour or longer if you spent 3 hours studying it, right? So what's the point of that? You're going to give it to some engineer and tell them, do it, right? Or actually, whatever you're going to do. You might have to do it at some point. But you can take that time, and I bet you can probably get it right. After all, you're MIT students. Yes?
Where would HY80 fall in the susceptibility index?
Well, it depends on the thickness and the restraint.
Well, I'm saying here, the weather codes, the susceptibility grouping?
Yeah, susceptibility, well, HY80, which should in the shipyard have an H1 level. Okay, right. So the first one, you would go to you're going to have excellent control of your hydrogen in a Navy shipyard. Okay, it's going to be like an oil rig shipyard. It's not going to be like some structural building yard. Okay, so in a critical structure like a pressure vessel or a Navy submarine or even a Navy ship, surface ship, you're going to be in the H1 category. So now you're going to look at your carbon equivalent. The carbon equivalent for HY80 is going to be probably between 0.38 and 0.5, so it's going to be an E level. Okay? If I come down here, and this is a panel line that I'm just taking small plates and making them into bigger plates that I'm then going to cut up, I'm going to be at low restraint. So if I had E level on a panel line, if I have E level and I have 3/4 to 1.5 inch thick, I got to have a 230 degree preheat. If I'm up to 3 inches, I might have to have a 250 degree preheat for HY80 or HY100, typically. So you can see lots of preheat with HY80. If I was HSLA, if I was a surface ship person, and I had HSLA, the HSLAs might be here in the C or D region. Some of them, thinner ones, might even be in the B region. So how much preheat can I tolerate? If I'm on a panel line without much restraint, I'm going to be B, C, or D, and in the thinnest regions, like a surface ship, I don't have to preheat. I told you, that's what happened in the shipyards. They didn't have to preheat. If you're at 1.5 or 3 inches, up to 3 inches thick, you might have to have 100 or 200 degrees. In some cases, if you're really low carbon equivalent, you wouldn't be low carbon equivalent in general if you're this thick, okay? But you can see, you can get rid of a lot of preheat, okay, on the HSLA steels that would ordinarily in the HY80s would be up in the over 200, well over 200. Big dollar savings. Tens of millions of dollars per ship because of preheat, okay? And if you're now down into some bowels of the ship where now these little sections have been cut up and now I have to preheat these even higher because of the high restraint, I go from 250 to 320 in most cases, most thicknesses. And for the E, I might be well, I'm still at kind of 280 to 320. I still, with high restraint, I still have to use a lot of preheat. Does that answer your question?
It does. Thank
okay? But you can kind of see how HSLA steels can save tens of millions of dollars per ship. And so the surface people use them and the subs don't, because the sub people are conservative, okay? Why are they conservative? They believe that there's not enough history on the toughness of the HSLA steels. They don't have all the work that was done in the 50s and 60s on the explosion bulge test. I showed you the explosion bulge test that Polini did. They basically take it underwater and they make a weld and they hit it with an explosive charge and they get all those shock waves from the explosion and they see if the thing will deform. You know, if you get a hole in a surface ship, hopefully you just plug it with a bunch of, well, we saw pictures of people plugging holes, right, on surface ships, okay? On a submarine, you get a hole and you probably lose the ship, a big hole, and you probably lose the ship, just because by the time you could plug something that thick and that high of pressure, you've already flooded most of the thing and it's just going to be going nose down or tail down. So there's a reason why the submarine people are more conservative. Plus, I think strategically, they're part of the triad of nuclear deterrent. And whenever you're talking about nuclear stuff, you're talking big bucks, right? Okay. Which, I don't know if I, well, I do want to take a little time. I won't, well, I'll say it even though it's on. One of the people at Sandia National Lab, which is the custodian of the safety of all our nuclear arsenal, he told me, he asked me once, he said, well, you know why we spend so much money on nuclear weapons? I said, no. He said, because it's used to be about $40 or $50 billion a year to run the nuclear labs, which is actually mostly DOE money. It's not actually Defense Department money, but it really is defense spending. And the reason, he told me, which it makes sense if you think about it, it's a little gruesome, is it's the cheapest way to kill someone, okay? The number of people you kill per dollar is the least with nuclear weapons. Okay, now we've only been used them twice in the world, fortunately, but it is the lowest dollar cost to kill someone. And that's why we spend so much money. Now, what I want to do in the next couple of minutes, because we don't take the whole time for the presentations, half an hour per presentation, we haven't been. I want to go through a welding procedure, okay, as the structural welding code. It's similar if you're in the ASME code. In the back, they will have forms for WPS, a PQR, oops, and certification. These are different things, okay? A WPS is a welding procedure specification. And these acronyms are used not just in the United States, but in lots of parts of the world. A PQR is a procedure qualification record, and certification is qualifying the welder, the person. So I always like to give you the analogy of you want to bake a cake. This one, the first one, WPS, is the recipe. You know, it could be Betty Crocker, it could be Pillsbury, it could be your grandmother. There is some recipe for making a vanilla cake, okay, or whatever type of cake. Different type of steel, it's a different flavor cake. So you have different WPSs for different steels. It's the recipe that you must follow. The procedure qualification is you now must bake a cake and show that the cake comes out like you expect. It doesn't fall, it's cooked all the way through to the middle, it's not burned on the outside. So you actually have a qualified welder make a weld, and then you test the weld by whatever means the engineer says you have to test it to get qualification. You actually bake the cake and test it. So we all get to eat birthday cakes, okay, whatever. Okay, and the certification is you're going to have more than one person do all the welding. It's not just the person who did this qualification test. You're going to have hundreds of people. If you go to, anybody know what the largest welding facility in the United States is, has more welders than anyone else? It's not a shipyard. Caterpillar, Peoria, Illinois. Okay, they got about 5,000 welders in Peoria. Okay, but they weld big, heavy steel pieces and stuff. The welder has to be certified. Okay, and they have to show they have the skill. One of you asked, well, we get to practice welding. Well, yeah, you can practice welding. Those who actually have been doing welding know that it takes more than an hour or two to become a welder, and we might set up something so you can go down there and learn how to stick the electrode on the plate, because that's what most people do for the first hour, and then they get frustrated. By stick the electrode, you have to start a stick electrode by what we call a scratch start. You basically bring it in, just gently touch the surface and pull it away. If you don't do it gently enough, you end up welding it, and you're sitting there trying to pull it off. And you'll find how strong a little spot weld really is as you're trying to pull it off. And it's sort of humorous to go through, isn't it? To watch new welders learn how to do it, and they're sitting there trying to pull the thing off. I did it, as far as that goes. In any case, so if I go to the back of the structural welding code in Annex N, they give me a typical welding procedure specification. This is the form, okay? And it tells me all the things that I might have to fill in to have the recipe. The name of the company usually owns the welding procedure. It's part of their proprietary information. Welding process, gas tungsten arc, shielded metal arc, submerged arc, electron beam. Supporting PQR. What was the test that supports that this recipe is a valid recipe? Okay, so you don't just have a WPS. You have up here, was it qualified by testing, which is a PQR, or was it pre-qualified by something else? We'll talk about that. This is the company's ID, revision, date, blah, blah, blah. Okay, that's sort of clerical stuff. Joint design used, base materials, filler metal, shielding, preheat, position, electrical characteristics, techniques, post-weld heat treatment. Down here, the welding procedure, pass or weld layers. It might be a multi-pass weld, the process, and you have to give all this kind of detail. And then they give you a typical version. And when I worked for Bethlehem Steel, they gave me, as a welding engineer, a notebook of all the Bethlehem Steel welding procedures for their structural welding division. And it had things like this, just page after page. It was exciting reading, okay? But if I had a particular type of steel, I could look up the type of steel. I could look up the process. I could go down, and it would tell me same type of thing. If I'm a welding engineer, I ought to be able to write one of these things. You're not welding engineers, so don't expect to write one. Go hire some welding engineer to do it for you. Someone who graduated from Ohio State or something like that. Okay, this tells you actually how many inches per minute and amps and everything. So this is a typical what they tell you you should have. Almost everything's filled in, very few blanks. It's not a tungsten process here, so they didn't fill in that. This is one you have to interpass cleaning. You got to remove the slag. There's no post-weld heat treatment on this. Preheats are up to 150 degrees with interpass temperatures between 150 and 300. However, if you go to the structural welding code itself, there's a whole section, I think it's chapter 2. They keep changing things in the chapters, but it's chapter 3 now, so I told you. It used to be chapter 2. There's a whole set of pre-qualified welding procedures. So what it means is, in the old days, like before 1950, every company had to have their own recipe, they had to have their own PQR, and they had to certify every welder. So the recipe might have a welding engineer, might cost $1,000 or $2,000 to have a welding engineer develop a welding procedure specification. To test the welds might cost $1,000 to test and prove out a weld. To certify a welder might cost $500, and you might have to certify 20 or 30 or 100. So this was proprietary information for the companies, and it kept other companies from being able to bid on projects if they didn't have their own set of welding procedures and specifications. So at some point, the Structural Welding Code said, this doesn't make any sense. Some of these things are sort of standard procedures. How do you make a fillet weld on A36 steel? Well, we do that all the time. So they wrote up pre-qualified procedures. And this is what the American Welding Society, when they have to write up a pre-qualified procedure, everything fits on half a page. And basically, most of the information you need for simple welds is here, rather than the page before that had a whole page of all kinds of detail, right? Because if it's simple steels, and that's what this is for, you don't have to have all that other information. It's when you get to the alloy steels and the heavy sections. But for bridges and buildings, we're not usually talking more than 1 inch thick. The base metal thickness be 1/4 inch minimum by different processes to unlimited thickness. That can get you in trouble. Some people go to the Structural Welding Code and say, I'm going to use this for 8-inch thick steel. This is for structural welding, which is rarely over 2 inches thick, rarely over 1 inch thick, okay? And root opening, groove face, so they're telling you how closely these things have to fit together. And there's lots of other things in the code, but they can write it in a very abbreviated form. So what happened was, actually in the early 90s, people said, well, it's good to have some pre-qualified procedures, but we need more, we need to simplify this certification. And we want to essentially provide a certification so an individual who wants to qualify doesn't have to re-qualify when he changes companies. It used to be if you were working for Caterpillar and you had to move to Iowa, in Peoria, and you had to move to Iowa, and you got a job with John Deere, you had to be retested at a cost of about $500 because you had to be qualified by your employer. And they said, this is, some people, particularly in the oil field, some guy starts working on one job and then 6 months later he's working for another company, goes work for somebody else. Every 6 months he's working for someone else, he has to be recertified. The guy's been welding for 30 years, and it's costing $500 every time to certify him or more. So the American Welding Society says, we will certify welders. And you can get a little card from the American Welding Society. You have to go to a testing facility, which will be approved. Here in Boston, you can go down to Triangle Engineering is one of the approved testing facilities. They probably have a half a dozen others, but Triangle was one of the first down here south of Boston. And you have to pay the American Welding Society a fee. It might be $1,000. And you can take the test, you can make the weld, they will break it, and they will determine if you pass, and if you pass, you will get a card saying you're a certified welder. And you can take that to any company you want and show them your card. Okay? Sort of like a driver's license, a welder's license, if you will. American Welding Society is making $10 million a year profit on this now. Okay? They used to be squeaking along on $1 million or $2 million a year. Now they're got 10 or 15 million a year. Just built a brand new Taj Mahal down in Miami. They got all kinds of money. Most of it goes into the AWS Foundation to help educate mostly, some people at universities, but mostly at trade schools to produce more welders. So we have a good supply of welders. Then in the mid-90s to 2000, they decided, well, we will develop some pre-qualified welding procedures. And the ASME code started doing the same thing. When they saw the American Welding Society do this, they said, we got to get in on this. We can't afford to have them start having pre-qualified procedures. That will mean that some people will start trying to use their code rather than our code. So we want to get in on this. So both of them started pre-qualified welding procedures. And so if you want to spend $1,000 or $2,000, the AWS will sell you a pre-qualified code. And this is the code, May 28, 1996, Standard Welding Procedure Specification, WPS, shielded metal arc of carbon steel, and here's the different types of steels, okay? And then you have to go to the code to understand what those are. 1/8 inch through 3/4 inch thick, E6010 electrode, one of these cellulose electrodes, vertical uphill followed by E7018 vertical uphill as welded condition, primarily pipe applications. So this is what a plumber uses to put black iron pipe into some, you know, big boiler or something, just to weld carbon steel pipe. And they can buy this, and it basically is pre-approved, pre-qualified. Yep. What do I have to do? Okay. It's pre-qualified. AWS qualified it, and it is a welding procedure specification and tells you everything you need to do, except when they do this, first of all, okay, statement of use, and they have their copyright. They're the people who helped write it, okay, lots of people prominent in the industry. A forward, okay. This one was actually developed by the Welding Research Council, oops, supporting PQR numbers, and there's a bunch of PQRs that support this WPS. And you can go through, this is 10 pages long, as I remember. 13 page. Looks like it might be 13 or 16 pages long. Goes through in excruciating detail, okay, and tells you every little thing you would need to know about how to weld a piece of black iron pipe, okay. So AWS is now making, like I say, over $10 million a year by providing all of these services in most cases. But if you got a new steel or sort of a special application, you still may have to develop your own welding procedure specification and your own PQR. So some companies still do things, like if you're doing overlay or something, AWS has only developed these they've developed them for aluminums and nickel alloys and steels. They continue to develop them, but they're spending tens of thousands of dollars on each one of these to develop it, but then they're selling it for hundreds of thousands. Not a bad business, right? So that's how things have changed in the last 20 years. And they've done it to streamline things and simplify things, and end up with better procedures. Okay. So why don't we take a break until 8:43 or something, and then whoever, let's see, Jago? Jago? Okay, if you want to be first.